We're going to discuss nuclear fission first. Let's get a couple of definitions out of the way. In a nuclear chain reaction, one nuclear event leads to additional ones. You can think of setting up dominoes on a table, stacking them, and you tip the one on the end, and that's kind of what we're talking about with regard to a chain reaction. And there are two other terms, fissionable and fissile, that are often confused. Fissionable means is able to undergo fission. So anything that can split into two smaller bits is fissionable. Fissile is more specific. Fissile means is able to sustain a fission chain reaction. And fissile materials are really the ones that we're most interested in if we're going to do useful work with fission processes. All fissile substances are fissionable. All fissile substances are able to undergo fission. But not all fissionable substances are fissile. A fissionable substance that is not fissile can be induced to undergo fission, but then it won't sustain a reaction. It will, pardon the pun, fizzle out unless we bombard it with something else. Fissile materials are the ones that we're most interested in. And there are, frankly, not very many fissile materials. Not many important ones, certainly. Here are the most important ones. Fission probability increases when we have slow-moving neutrons. So let's talk about that process of fission here. If we have a nucleus, and on the left we have a fast-moving neutron, it hits that nucleus. Basically, nothing happens. Fission generally won't occur. On the other hand, if we have a slow-moving neutron, here's what we think happens with the nucleus. The nucleus will deform just enough that the two halves of the nucleus, or two of the larger parts, become too far apart, and it turns out that the nuclear strong force, which holds the nucleons to each other, becomes very weak if the distance becomes too large. So what happens is the positive repulsion takes over and the parts of the nucleus repel. That's the process of nuclear fission. Often in fission, some free neutrons are released, and in fissile materials, those often induce other fissions, and we can get a chain reaction going. The critical mass is the mass of fissile material required to maintain a chain reaction at a constant rate. Supercritical mass is the minimum mass for which the chain reaction will accelerate. If we have 4 samples of fissile material, this one is lower than the critical mass. Even though it's a fissile material, we will not be able to sustain a chain reaction. This one apparently also is below the critical mass. We can't sustain a chain reaction. That would be the critical mass, which is the amount that's required to maintain the reaction at a constant rate. In other words, it won't be speeding up, but it won't be slowing down. It'll be proceeding at a constant rate. And if we have more than that, that would be a supercritical mass, for which the chain reaction will accelerate. And at that point, it's time to run, Forrest, run, because something possibly could happen. The first atomic weapons, quite simply, the process was to take 2 subcritical masses, one at each end of this bomb. You can imagine close to us here a subcritical mass of fissile material, and at the far end another subcritical mass. All that was required was to join those two subcritical masses that together would produce a supercritical mass. And that's it. That's how those first atomic weapons worked. Let's turn to fusion. Nuclear fusion processes are also called thermonuclear reactions. You should know you cannot pretend to be a human being unless you know that the stars are powered by nuclear fusion, in which basically hydrogen nuclei, or protons, are converted into helium and produce energy. The good thing about fusion is that products are generally not radioactive. It does require very high temperatures, which is not a problem on stars, but it is a problem on Earth. We're talking millions of degrees required in order to start a fusion reaction. And the reason for that is because the nuclei are all positively charged. If they're moving slowly, as soon as they get remotely close to each other, they're just going to repel. You've got to get them moving fast enough that they actually get close enough to each other so that the strong force takes over and outweighs the positive electrostatic repulsion. On this planet, there aren't any ovens, there aren't any jars, there aren't any barrels that can handle millions of degrees. Research into controlling fusion continues. Of course, uncontrolled fusion, we call that the hydrogen bomb, and that isn't really doing any useful work. So what we're trying to do is use magnetic fields to contain and heat fusion reactions. We haven't figured it out yet, but hey, after you finish watching this video, feel free to go out and do that, win a Nobel Prize, and help mankind. Let's summarize. Fission is the splitting of larger into smaller nuclei. Only certain radionuclides are fissile, and thus useful in practical applications of fission, which require chain reactions, such as nuclear power reactors. Fission is best initiated by slow-moving neutrons. A fission reaction will start spontaneously and continue reacting if a large enough amount, the critical mass or supercritical mass, of fissile material is accumulated. Fusion, which powers the stars, requires extremely high temperatures in order to overcome the electrostatic repulsive forces between positively charged nuclei.